Folks, this is a lesson about solving linear, non-homogeneous, constant coefficient equations. And we're going to get to the kind of concrete nitty-gritty about how to do this before too long. But first, to help you understand why the procedure is what it is, we're going to do like just a tiny little bit of theory and new ideas. So start by remembering that a function, or a function of one variable, is something where you plug in a scalar x, and then you get out f of x, right? So just as merely one example, it could be that you plug in x and the function multiplies it by 3 and adds 7 and then spits out that value, right? So that's how I want to think about a function. It spits something out when you give it an input. Similarly, instead of thinking of scalars, we could think of functions as the inputs. And there are these things called linear operators that do something to the function. They take the function, they operate on it, and they spit it out. And it's called a linear operator because the thing it does is linear. So to give you one example, say we plug in a function of y of t here, and the linear operator could take that function and differentiate it twice and multiply it by 7. And then it could differentiate once and multiply by 9 and subtract that. And then it could take the function without differentiating at all and multiply it by 2 and add that. That's an example of a linear operator. And one thing we can do is write the kind of equation we are thinking of in terms of a linear operator. So, I want to think of this differential equation here, y double prime plus py prime plus qy equals f of t. And an alternative way to write that is as the linear operator ly, the linear operator L operating on y, and that's the left-hand side, and then the right-hand side is f of t. It's just shorthand for the same thing. So what the linear operator L is in this case is it means differentiate twice, differentiate once, multiply by p and add, and then just take the function itself and multiply by q and add that on. That's the definition of our linear operator here. And so here's going to be our strategy for solving this differential equation. And I'm going to purposefully repeat myself and say the same thing a bunch of times. The strategy is basically going to be to think of this picture here, right? This kind of linear operator picture. And you want to find the solutions where when you plug it in on the left, you get out f of t, right? That's what this equation means. And the way you're going to do that is first you're going to find all the stuff that gives you 0. That's right. All the stuff where when you plug it in, you get out 0 on the right-hand side. Then you're going to find all the stuff where when you plug it in, you get out f of t on the right-hand side. And the full solution to the problem is the sum of those two things, right? You can toss in as much stuff over here as you want that gives you out 0, and then you can toss in stuff that gives you out f of t, and you're allowed to add them because it's a linear problem, right? And linearity means that there's this superposition principle that we've talked about before. So I'm going to say this again. The first problem that you solve is this problem here. It's LYH equals 0, and the subscript of H, the H stands for homogeneous. So this means I'm solving the homogeneous problem. I took my original problem, but I threw away the inhomogeneity, and I solved that. So that's all the stuff where when you plug it into L, you get out 0. Then you solve this problem, right? LYP equals f of t, where y of p is called the particular solution. And then the full solution to this problem is the sum of these two things. And you're like, but Chad, if y of p gives you out f of t, why do you need the other stuff? And the answer is because if you just have the particular solution, it's not the whole solution to the problem. It's only part of the solution. And, if you want to see this, just think of applying the linear operator L to that full solution y, right? L operating on y means L operating on YH plus YP. Since it's linear, by definition, that means L operating on YH plus L operating on YP. L operating on YH is 0 since it was the homogeneous solution. L operating on YP is f of t since it was a particular solution. And 0 plus f of t is f of t. So again, I've kind of proven to you here that the sum of the homogeneous and particular solutions is a solution, or the solution, to the differential equation that we're trying to solve. Now, in terms of how we're going to do this, you know how to solve the homogeneous problem already. You do the characteristic equation. The technique that's going to be new for today is finding this particular solution to the inhomogeneous problem, and that's going to be using a method called undetermined coefficients, which is basically just intelligent guessing. So here's how it works. We're going to take this problem as an example. It's y double prime minus y prime minus 6y equals t cubed. So step one, first we solve the homogeneous problem, so we've set the right-hand side to be equal to 0. We write down the characteristic equation, we factor it, and we find that lambda can be -2 or 3. And I'm purposefully going through this a bit briskly because this was a technique from the previous lesson. So you have these two values of lambda, and you construct then the solution to the homogeneous problem. It's a linear combination of the two fundamental solutions in the fundamental solution set. So that's the homogeneous solution. Now we've got to find a particular solution that solves this equation here, right? Now we're keeping the inhomogeneity. And here's how you think about it. You say, well, on the right-hand side, the inhomogeneity is a polynomial. That's the class of functions it is. And you say the only way to get out a polynomial by plugging into the left-hand side linear operator, the only way to get out a polynomial is by plugging in a polynomial. So I've got to guess that yp is a polynomial. And if you think about it for a second, since differentiating a polynomial only makes it be lower degree, the thing I have to guess for y, if I want to get out a cubic polynomial, is I have to guess a cubic polynomial. So I guess that yp is a cubic polynomial, but it's a general cubic polynomial with undetermined coefficients. And our job is going to be to figure out the coefficients by plugging it into the equation and kind of enforcing that it's a solution. Before we plug in, it's helpful to pre-compute the derivatives. So, I've calculated yp prime and yp double prime for you here by differentiating this kind of general cubic polynomial. And now we take all that and we plug it in. So yp double prime minus yp prime minus 6yp has to equal t cubed. That's the original equation. I'm going to take the left-hand side and plug in our guess for yp, and that gives rise to this messy expression here. You have a polynomial on the left, you have a polynomial on the right. What your job is to do is to guarantee that those polynomials equal each other. Two polynomials are equal if and only if the coefficients of each term are equal. So you look at t cubed terms, you looked at t squared, you look at t to the first and t to the 0, and if you equate the terms on both sides of the equation, you get this system of 4 equations and 4 unknowns here. You solve it using your favorite technique, and you find the values of a, b, c, and d. And then the final step is we invoke linearity, meaning that the final solution to the equation y is the sum of the homogeneous solution and the particular solution. So that's our pair of exponentials plus this cubic polynomial that we found here. Here's another example. It's going to be the same linear operator on the left-hand side, same as previous example, but my inhomogeneity now is going to be cosine of 2t. So step one, solve the homogeneous solution. Well, that's the exact same as before. It's the same homogeneous problem. Step two, find the particular solution. And since this is a cosine function, the guess that I'm going to make is trigonometric functions. I know that differentiating a trig function, if I differentiate cosine or sine, I get a sine or a cosine. Differentiation doesn't change the frequency of the function, so I'm going to guess as my particular solution this combination of cosine 2t and sine 2t, where the coefficients a and b are unknown. And the way I'm going to find them is by plugging them into the equation. So I pre-compute these derivatives, yp prime and yp double prime, and I can go ahead and plug in, and if I plug in, I get this boxed equation here, where the left-hand side is what comes from plugging in our guess, and the right-hand side is the inhomogeneity, cosine 2t. Well, the only way the left and the right-hand side can be equal is if the cosine terms are equal and the sine terms are equal. So I look at cosine terms here, I look at the sine terms here, right? And this gives rise to two systems of equations and two unknowns. I solve them, and I get these equations for a and b. And then the last thing that I have to do is to invoke linearity. So I add the homogeneous solution and the particular solution. Homogeneous solution is what it was before. Particular solution is what we found right above. All right, so that's it for this lesson, but I'll just wrap up by commenting that we worked here with a second order homogeneous or inhomogeneous constant coefficient equation, but there's nothing special about second order. The same technique works for equations of higher order, and you can try that out yourself. I'll also say that in terms of what to guess for your educated guess in the undetermined coefficients problem, you'll get more experience as you solve problems feeling what the right guess is, or you can look up many helpful tables, online or in a textbook that say, if the inhomogeneity is of this form, then here's the form you should guess. But I honestly just prefer to try to use some logic and intuition. You're welcome to do whatever you want. Okay, thanks for listening.